Scientists harness a single molecule to probe the atom's core. Scientists harness a single molecule to probe the atom's core for decades. Physicists have sought to unlock the secrets held within the nucleus of an atom, traditionally employing massive and complex particle colliders to bombard nuclei with electrons. These facilities, often spanning kilometers, accelerate electrons to incredibly high speeds in a quest to understand the fundamental building blocks of matter. However, a new study proposes a radically different approach, utilizing an atom's own electrons as miniature messengers within a single molecule, creating a novel way to study nuclear interactions without the need for enormous infrastructure. A molecular collider, the research team's innovative technique, involves pairing a radium atom with a fluorine atom to form a radium monofluoride molecule. By leveraging the unique properties of this molecular structure, they generated a microscopic collider, where the radium atom's electrons momentarily penetrate its nucleus. Researchers were then able to precisely measure the energies of these electrons within the molecule, revealing subtle shifts that indicated the electrons were, indeed, briefly entering the nucleus and interacting with its contents. Unveiling nuclear symmetry violations, this breakthrough holds significant potential for measuring the magnetic distribution of a nucleus, also known as how its arrangement of protons and neutrons influences its magnetic properties. The team emphasizes that this research represents an early step, but they anticipate using this method to gain new insights into the radium nucleus and, ultimately, to address some of the most profound mysteries in physics. A persistent puzzle in cosmology is the stark imbalance between matter and antimatter in the observable universe. Current models suggest that the very early universe should have contained roughly equal amounts of each. However, antimatter is remarkably scarce today. Scientists theorize that clues to this asymmetry might reside within the inner workings of certain atomic nuclei. Radium stands out as a promising candidate due to its unusual, pear-like shape, an asymmetry that may amplify the potential for observing violations of fundamental symmetries. Challenges and future prospects. Despite the promising results, researchers acknowledge the challenges associated with studying radium. As a naturally radioactive element with a short lifespan, radium monofluoride molecules can only be produced in tiny quantities, necessitating incredibly sensitive measurement techniques. When you put this radioactive atom inside of a molecule, the internal electric field that its electrons experience is orders of magnitude larger compared to the fields we can produce and apply in a lab, explains Silviu Marian Udrescu, a physicist at Johns Hopkins University. In a way, the molecule acts like a giant particle collider and gives us a better chance to probe the radium's nucleus. By confining and cooling the radium monofluoride molecules and then utilizing lasers to measure electron energies, the researchers were able to detect subtle shifts in the data indicative of nuclear interactions. We now have proof that we can sample inside the nucleus. It's like being able to measure a battery's electric field. People can measure its field outside, but to measure inside the battery is far more challenging. And that's what we can do now, says MIT physicist study co-author Ronald Fernando Garcia Ruiz. This discovery could fundamentally transform how physicists study atomic nuclei, opening new avenues for exploring the fundamental symmetries of nature. The research team is optimistic that radium-containing molecules will prove to be exceptionally sensitive systems for searching for these symmetry violations, and they now possess a novel tool to carry out this search.